Welcome to Eureka Math. I'm Mr. Shankel. I'm going to be helping you today with Module 2, Lesson 18, and this is Part 2. Let's get started. In the last lesson, we talked about finding the greatest common factor by making lists, and we found that it's difficult to get lists that are complete so that we don't miss a greatest common factor, and that's the downfall of finding the greatest common factor with lists. For example, if you had to find the GCF of, let me make that a G, GCF of 48 and 60, then you would have to make a list of all the ways that you could multiply to get 48. So that would be 1 times 48 and 2 times 24. And let's see, 3 times 16. That would be an easy one to miss. 4 times 12 might be one that you would miss. And then 6 times 8 is also a way to get 48. Okay, so there's some tough ones in there you might not remember or even know. 60, that would be 1 times 60. And then 2 times 30 works. And then we have 3 times 20, that would work. 4 times 15 is 60. You might not have had that one. This one's missed a lot. 5 times 12, that's 60. So that could be missed. And then 6 times 10. Well, there's definitely some factors in there that I could just forget or not know or realize. And the problem with this particular GCF problem is if you forget that 4 times 12 is 48 or 5 times 12 is 60, you're not going to get the right GCF. In other words, you can see here that the greatest common factor is 12. But if you didn't have either one of these, 4 times 12 is 48 or 5 times 12 is 60, then you might think incorrectly that the GCF is 6. But it's not, we know, because there are 2 12s here. So really difficult using lists to get a complete list to make sure that you find the GCF. So there's got to be a better way, and there is. Let me show you the way that it works. Let's use 48 and 60 again, only this time we're going to use something called prime factorization. And what we're going to do is we're going to break these numbers down into only their prime number factors. So I'm going to take this 48 and this is called a factor tree. I'm going to just start dividing this. And it doesn't matter how I do it, just that I eventually end up with all prime numbers. So I know that 48 is even, so I'm going to say 2 times 24 is 48. So those two numbers multiplied together equal 48. And I know that 2 is a prime number. So I'm going to circle it. 24 is not a prime number. I can divide this. 24 can be divided into 2 times 12. And again, 2 is a prime number. 12 is not, so I'm going to keep going. 12 is 2 times 6. 2 is prime. 6 is not. 6 is 2 times 3. And 2 is prime, so is 3. I can't divide that by anything else. So now I have all of the prime factors of 48. If we multiply these back together, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3 is 48. So we get back to our original number. Okay, let's do the same thing with 60. 60 is 2 times 30. 2 is prime. 30 is 2 times 15. 2 is prime. 15 is 3 times 5. 3 is prime, and 5 is prime. You can't divide 5 by anything else other than 1 or itself. So now we want to find the factors that are common in both lists here, both factor trees. And I see a 2 here is common with a 2 here. And this 2 is common with this 2. And let's see, there's no other 2's in the 60 list, so can't use any of those, but there is a 3, so that 3 is common with this 3. So now I have factors, prime factors, and I have the common prime factors. In order to find the GCF, I take these two, all of these common factors, and I multiply them back together. So we're just going to split. I'm having a system failure here. There we go. I'm going to take the 2 times the 2 times the 3. This 2, and that 3, the ones that were common, multiply them back together to find that the GCF is 2 times 2 is 4 times 3 is 12. The GCF is 12. And I could find that on the other side as well. 2 times 2, 2 times 2 times 3. 2 times 2 is 4 times 3 is 12. So prime factorization does something for us that the list does not. It keeps us from missing a factor and getting a wrong answer or an incorrect GCF. Okay, so that's the first part of our work today. That was using prime factorization to find the greatest common factor. Okay, the next thing we did was, well, we took an addition problem. Like, let's see, we took an addition problem like 12 plus, I don't know, 30. We took that addition problem, and instead of just adding 12 plus 30 is 42, we have to write this using the distributive property. And I know that you're probably saying, why don't we just add 12 plus 30? Because that seems a little easier. The answer is, eventually the distributive property is going to be really important in future math work. So we're going to practice with numbers that are easy now, so that when we get to algebra and variables, it won't be as daunting and difficult. So what we're going to do is find the GCF of 12 and 30. So that's my first job. I'm going to find the GCF of 12 and 30. So I'm going to use prime factorization since we practiced that today. 12 is 2 times 6. 2 is prime. 6 is 2 times 3, and those are both prime. So there's 12. 30, well, a lot of ways I could do this. I could maybe 5 times 6. 5's prime. 6 can be 2 times 3. Prime, prime. As long as I can get down to prime numbers, it doesn't matter which way I get there. I could have divided by 2 and said 2 times 15 and then 3 times 5, but I get the same prime numbers anyway. Okay, so what are common? Well, I see a 2 here and I see a 2 here. Those are common. And here's a 3 and there's a 3. So my common prime factors are 2 and 3. I have to multiply those back together to get the GCF, which is 6. So my GCF is 6. That means I'm going to write this addition problem as multiplying by some factors without a common factor. So here's what we do. The GCF comes outside of the parentheses. What we're doing is we're dividing the common factor, the greatest common factor, out of the two terms. So 12 divided by 6 is 2. We have a plus sign, And then 30 divided by 6 is 5. And what we've created is a common factor right here. That's too much. There we go. A common factor times a sum that has no common factor. So this sum has no common factor in it. And in this way, we're able to create a multiplication problem between the common factor 6 and the sum of the terms without a common factor. You might be thinking, wow, I guess that's all right, but what's the big deal? Why so important? Well, when we get to things like 2x cubed plus, 8x squared, we can't add those because x cubes are different than x squareds. So I can't just say 2 plus 8 is 10. We have to have another way that we can solve problems. At this point on that problem, I can't solve it. I need to be able to set it equal to whatever this might be over here. Maybe it equals 3x. Who knows? Could be anything. But right now I can't solve that problem. The only way that I can solve that problem is to use the distributive property and find a common factor. Right now, the common factor between these two is a 2 and an x squared. So the common factor is 2x squared, and then I can divide. 2x cubed divided by 2x squared is x, plus 8x squared divided by 2x is 4. And that would equal whatever this is. So then I could say, I know I'm probably getting into things that don't really matter yet, but there's a reason that we're doing this, and that is, I could say 2x squared is equal to 3x and solve for x. And then I could say x plus 4 is equal to 3x and solve for x, and I can get some answers to this problem. Otherwise, we're stuck. So the distributive property will be used a lot as you move forward into some higher level math, and we need to learn how to use it now with some easy numbers, because I think you'll agree that this isn't quite as easy as this. Okay, so we're pulling out the greatest common factor, and instead of multiplying it in, we're dividing it out. One more thing I wanted to show you. You could take this and multiply it back in. 6 times 2 is 12, and 6 times 5 is 30. So I get right back to my original addition problem. So in essence, we are using the distributive property by multiplying in and then dividing back out a common factor. All right, that's the end of lesson 18. I hope that helps. I'll see you again next time.